that is where this shape becomes so important, because it's a direct correlation between what the lithium looks like and the eventual battery performance.
This is the Discovery Files podcast from the U.S. National Science Foundation. I'm Nate Potker. Renewable energy, sustainability, and global climate change are among the grand challenges of the 21st century. Our guest today is Yuzhang Li, assistant professor in chemical and biomolecular engineering at UCLA, whose Li group is working to develop novel materials chemistry and state-of-the-art tools to enhance our understanding and the performance of electrochemical systems, which would directly impact these renewable energy and sustainability goals. Thank you so much for joining us today.
Thanks, Nate. Happy to be here.
So I'd like to start with some of your early interest. How did you get interested in chemical engineering?
Well, I mean, to be honest, I actually came in at undergrad as a bioengineering major, and realized that I didn't really I like the concept of doing biology, but actually doing research and tissue culture was just not for me. I loved the concept, learning about it in class, but decided chemical engineering was the path. And I think actually, if I'm further honest with you, I took a look at the salaries of the chemical engineers go to petroleum companies traditionally, and that was my initial motivation and attraction towards chemical engineering. But further on, as I learned more and more about chemical engineering and just the foundational concepts like transport, kinetics, thermodynamics, and how it can be applied to so many different things, that allowed me to grow more fondly of this whole discipline of chemical engineering. And so now I feel it's gone full circle. Now I teach chemical engineering in undergrad here, and I like to share them that experience from myself. My
right, it makes you a lot more relatable.
Yeah.
If you can kind of, here's what my journey was a little bit. So talking about that kind of schooling era still, your PhD, you were focusing on batteries.
Yes.
How did you get interested in batteries?
Yeah, great question again. So I remember my first experience in like this whole energy area was starting from an internship that I had with British Petroleum, not doing petrochemical things, but rather biofuels. They had this new area in biofuels. I was really interested in renewable energy. And while that experience was really formative, I think maybe I'm just biology was not for me. But I really appreciated the need to kind of transition our energy from non-renewable sources to renewable sources. So when deciding what to do in grad school, I kind of had two directions that I was thinking about. Harvesting the energy from renewable sources like solar and wind. There were some great researchers in solar cell technology at the time at Stanford, where I did my PhD. And also energy storage, how to store that energy when the sun isn't shining, right? And so decided to go for the energy storage route. And I majored in material science in grad school rather than chemical engineering, specifically to get that more atomistic, microscopic understanding of these phenomena that are critical to the operation of how batteries work.
And so from here, I think I have to ask you the most basic question with how batteries work. Mm-hmm. How do batteries work?
Yeah, great question. I think the easiest way I can try to explain it is we kind of know how chemical reactions work, right? At a fundamental level, there is some kind of chemical reaction, and usually there's energy released as heat. And although it's useful, we can't really utilize all of that heat energy efficiently. And that's because during a chemical reaction, there's two things that happen. There's an ion transfer and an electron transfer. Those two things happen in a chemical reaction. Now, in a battery, we basically decouple those. So usually the electron gets directly transferred from molecule A to B, but in a battery, we decouple that. We force the electron to go through an external wire or circuit. And that is the electron that we can harness as useful work. So by decoupling this ion and electron transport in batteries, this now becomes an electrochemical reaction rather than a chemical reaction. And so to put simply, I like to say that batteries hijack the electrons from chemical reactions in order for it to do useful work in laptops, cell phones, and electric vehicles.
So the next thing I'm thinking about is there a difference with rechargeable and kind of traditional batteries that come pre-ready in terms of like what they're made out of or how they're working?
Yeah, definitely. You're asking about the distinction between rechargeable batteries and maybe primary batteries, right?
Right.
Yeah, maybe this is showing my age, but I remember playing Game Boy a lot, right? And always there would be AA batteries, and I'd have to, pack extra batteries on vacation. And those batteries are not rechargeable because of the intrinsic chemistry that's happening. We could talk details about specifically what's happening, but intrinsically, those chemistries are not reversible, right? So you can't really recharge them, even if you tried. Now, fast forward to today, there's, these Nintendo Switches, these games, everything is lithium ion based because of the increase in energy density. So the battery lasts longer. And also you can recharge them because these reactions that are happening inside the battery are now reversible. You can go one way and the other with many, many cycles. So that's qualitatively what's happening. And we can talk more about the specific fundamentals if you want to.
I think that covered that bit fairly well. So the next bit I would like to ask you about is, we hear with rechargeable batteries about things blowing up. Like you can't ship lithium ion batteries at the post office, or you're not supposed to. They ask you about this. So what makes batteries volatile?
So this is a good question on safety, right? So right now, the lithium ion battery chemistries that's predominant is based on three major components, I would say, right? You have a positive electrode, you have a negative electrode, and you have this thing called the liquid electrolyte that allows the ions to move between the electrodes, but not the electrons. Now, things get dangerous, right? Remember I talked about batteries decoupling this ion and electron transport, right? If somehow the electron is able to pass through this electrolyte, then you have a short circuit. And that's when the electrochemical reaction goes back to being a chemical reaction. And you know what happens when chemical reactions happen: uncontrolled heat release, this positive feedback loop, right? So if I had to specifically talk about lithium ion battery fires, the liquid electrolyte is intrinsically flammable, right? This is an organic solvent that's not like water, right? Previously, batteries were aqueous-based, corrosive, but not intrinsically flammable. Lithium ion, they're intrinsically flammable. A lot of research trying to make it not flammable, but right now, commercially, they are flammable. So now how does it potentially short circuit? Well, the main issue is if there is some kind of pathway that electrically connects the positive and negative electrode, right? So somehow electron is able to pass through. This can happen a number of ways. The most common way is these lithium metal dendrites that you might hear in the media, right? So this is what happens when lithium ions, instead of going in between these nice layered materials in the anode, in the positive and negative electrode, instead of going in between these layered materials, now they start crystallizing as metallic lithium. And you can think of these filaments as kind of the dendrites that you see when ice crystallizes, right? It's very fast. And so if this metallic lithium goes through this electrolyte and touches the other side, that allows very efficient electron transport. And so that means that the decoupling of the electron and ion is no longer happening. That's when you have this chemical reaction happening. And that's basically how these fires and volatility comes about. I think the take home there is the electrochemical reaction in the battery going back to a chemical reaction as the key failure point.
Perfect. Thank you. So moving towards your paper, we've mostly talked about lithium ion batteries so far. You're working with lithium metal, which you sort of just mentioned is more conductive or kind of better if you could channel it.
Yeah.
Is my takeaway from what you said anyway.
Yeah.
So can you talk a little bit about what the difference between lithium metal and lithium ion is?
Yes. So let me talk about how lithium ion currently works and why it works so well, right? It can be recharged so many times without losing capacity. Why? Well, because these layered materials serve as our anode and cathode, right? So the way that lithium ion works is that you have these lithium ions going through the liquid electrolyte. And when it's charging, the lithium ions fit nicely in between the layers of carbon, right? This is our negative electrode. So we know graphite, as pencil lead, and there are these layered sheets of graphene, 2D materials, and the lithium ions fit nicely between these layered sheets. On the discharge, it goes back to the positive electrode, not graphite this time, but some kind of lithium metal oxide, mostly based on cobalt, but they are also layered materials where the lithium ion fits very nicely into. These are called intercalation chemistries that, are very, very reversible because the structure is not changing, right? And so if we want to increase the energy of our lithium ion, we actually have to remove this intercalation host, at least on the anode side, because the graphite is kind of dead weight. The actual material that's storing the energy is the lithium ion. So in a lithium metal battery, that's exactly what we do. We keep the cathode the same. Now we remove the graphite. So now you just have a copper current collector. And instead of intercalation into this nice 2D material, now you're doing what is called electrodeposition, right? So the lithium ion gets reduced by the electron and it forms metallic lithium. Normally this is not good, right, for batteries, but from an energy density standpoint, this is among the highest energy density battery chemistries that exist. And so that is the major distinction between lithium metal batteries and lithium ion batteries.
So in your paper, you're focusing on the shape of lithium.
Yes.
What role does the shape or form play in this process?
This is a great question. And to give you kind of context, this concept and this understanding of electrodeposition is more than a century old, right? This is a key process in industry to do coatings of metals. Copper is a very common model system, and we understand copper really, really well. But lithium is unique because it's so reactive, right? If you took lithium out and waved it in the air, it's going to immediately tarnish, right? It's going to react with the air very quickly. And so when you electrodeposit these materials in the battery, the shape becomes unpredictable, right? It doesn't fit any of the previous models that were applied to copper or other noble metals, right? Because of this reactivity. So then what is happening then? In lithium metal battery literature, very quick summary is liquid electrolyte, the chemistry of this liquid electrolyte really dictates the performance. And what battery scientists do, they'll look at the shape of the lithium that forms after battery operation. And they will say, hey, in electrolyte A, the performance is really good and the shape is really nice, right? Instead of these filamentary dendrite shapes, it's more like round, chunky pancake, right? And if you look in the literature, it's all of these qualitative descriptions of lithium because, our understanding of this electrodeposition process is so poor. And so our current understanding, or our previous understanding of this area, was if I change the electrolyte chemistry, I'm going to change the lithium shape, because the corrosion film that forms on the surface of lithium is going to be dependent on the liquid electrolyte, because that's the thing that's decomposing. You can think about it as a kind of rust. And so that is where this shape becomes so important, because it's a direct correlation between what the lithium looks like and the eventual battery performance.
So following from that, what's the benefits of knowing the shape? How will this help you make a better product?
Great question. So the first thing is, because of all of this qualitative description of lithium metal, the understanding of this electrodeposition process is incomplete. And what we really wanted to understand in this first project was, okay, there's been this challenge, right? Why does lithium metal electrodeposition not fit any of the previous models developed for copper? Is because of this corrosion film. We call it the solid electrolyte interface in batteries, this SEI layer. You can think about it as a rusting layer. And the difficulty is that when electrodeposition is happening, this SEI formation is happening simultaneously, right? And so what we wanted to do is, let's see what happens when we decouple this process, right? Can we electrodeposit lithium metal in the absence of this corrosion film formation? And what we discovered was, instead of these kind of random shapes that we actually don't really understand why it is the way it is, we see these very uniform polyhedra that are geometrically almost perfect, right? And we used advanced characterization techniques to really understand exactly what shape that was. And this is the so-called rhombic dodecahedron 12-sided dice shape. And we found that not only did it form in one electrolyte, but all of the liquid electrolyte chemistries that normally, deposit in these different shapes, when we decouple the deposition and the corrosion, it all converges into the same shape, this rhombic dodecahedron. And that's telling us that this is the intrinsic shape that lithium prefers to form under such conditions, and it matches theoretical predictions as well. And so then your question, so initially it was kind of an open question, right? What happens when we decouple this deposition and SEI formation? And this is what we found. And your question was, okay, how do we make a better battery? Well, initially we thought, hey, let's just, deposit these shapes and the battery is going to be perfect, right? Because we now avoid this corrosion. But actually, in our research, we found that a new kind of problem arise, right? Because these shapes, although they're really ideal, they're not like dendritic, they're not going to penetrate the separator. The contact between the lithium and the copper current collector is actually very poor. So what happens is, when you try to discharge your battery, when you want to use it, right, you won't actually get all of the capacity back, because this electrical connection is now broken, right? So, but understanding this failure mode will then give us more insight in the future. How do we maintain this electrical connection? That's ongoing work that we're pursuing in the lab. For this first paper, instead what we did was say, hey, the shape is actually very nice. So why don't we deposit these shapes initially as kind of nucleation seeds, right? And then as nucleation seeds, then eventually the lithium can grow in a more uniform and dense way. So instead of only forming these particles, we're kind of using them as seeds to grow later lithium. And that actually, in this paper, has shown a substantial improvement in the battery performance. But I will admit, nowhere near that level where we can say, hey, let's just start a company and commercialize this product. Yeah.
A little more work to go before you get to there.
Absolutely.
So you talked about decoupling and being able to kind of separate the corrosive process.
Mm-hmm.
Can you kind of talk a little bit about how you were able to do that? So if this traditionally lays down with corrosion, how do you make it so it doesn't?
Yes, great question. So our initial hypothesis was, okay, we don't know exactly how fast this corrosion process is, but just qualitatively, we know it's fast, right? So to decouple it, that means we have to electrode deposit, lay down this lithium metal even faster, basically outpace this corrosion reaction. And so to do that, we thought, well, why don't we just go ultra fast current density? When I say ultra fast, I mean values 10 times, 100 times, 1,000 times faster than what we would normally do, than what we normally charge our batteries with, right? But obviously, we can't just do this uncontrolled because we're going to meet mass transport limitations. There's this whole, whole set of details that I won't get into, but essentially, in order to avoid those mass transport limitations, right? You can think about it as a speed limit. In order to increase the speed limit, where above that speed limit, bad things happen. In order to do that, we now shrink the size of our electrode from being, maybe 1 centimeter squared to something that's very, very small, so that the local current density is very high, but the speed limit, we have much higher. So basically, we shrink the working electrode surface area so that we can go very, very fast without meeting this mass transport limitation. And that's how we were able to kind of decouple the corrosion process from this deposition.
Very cool. So I want to pivot a little bit and ask you about your career award. And can you kind of talk about the impact of NSF support on your career today?
Oh, absolutely. So I started my faculty in the summer of 2020, right? So it's a very
interesting timing.
Interesting timing. Taught my first classes virtually for the first year. And actually, my students didn't come until the second year. The following year in 2021 due to, travel restriction and visa. And so the first year, it was kind of unclear in terms of grant applications. As you know, faculty really, really need initial grants to continue their research. But when my first student came, we got these initial data of this very unique shape being observed in all of these different electrolytes. And that's really what helped craft the initial proposal for the NSF career. And I sent a white paper to the program officer, and they seemed interested and encouraged a full proposal submission. And luckily, we were awarded that first proposal so that we can continue this line of inquiry and research. And I would say that it has been transformative for my early career, just having that ability and confidence to keep going based on our preliminary results.
Fantastic. Thank you. So the last question I'd like to ask you is, what's next? You talked about kind of refining the process a little bit, but where are you going with research?
So I would say that there's 2 general directions. Definitely, because we're in battery research, we want to continue to improve the performance. So now one direction is, how can we further leverage this phenomenon of this intrinsic shape of lithium metal to improve battery performance? One idea or one direction would be, how do we make sure that this electrical connection is not broken during the battery operation? And there are a number of ideas for this direction. Second direction is, I guess, more of scientific curiosity, right? I want to understand, first of all, how big can we grow these particles, right? Like in the microscope, you can see in the paper that they kind of grow maybe 2 to 5 micron. For comparison, that's 10 times thinner than your hair, right? A strand of your hair. So I want to see how big we can grow these things, because then if we can just grow one particle macroscopically in a battery, maybe that would be something we would want. I don't know. The second curiosity is, okay, there's been, I would say, over 2 decades of research in this colloidal synthesis community. And this is something I was kind of aware in my PhD. So this is an example of where previous learnings kind of color your future ideas. And so colloidal nanocrystal synthesis is so powerful because you can tune the shape of gold nanoparticles and other noble metal nanoparticles to any shape you want. Cubes, rhombic dodecahedron, octahedron, all kinds of shapes. And so I want to explore whether it's possible to take similar approaches and tune the intrinsic shape of metallic lithium. Can we, instead of this rhombic dodecahedron, which is cool, but may not have direct impact for battery, can we instead grow cubes of lithium metal? Because as you know, cubes pack really well, right? In free space. So if we can grow lithium cubes reversibly, that could also be, related to battery performance, but also this curiosity of, can you do it or not? This level of precise control over the morphology of lithium metal has just never been demonstrated to that degree. And so those are kind of the 2 general directions I'm looking forward to next for this specific project.
Special thanks to Yuzhang Li. For the Discovery Files, I'm Nate Podker. Discover how the U.S. National Science Foundation is advancing research at nsf.gov.